Now we want to see the effect of boundary conditions on the wave patterns that we observe for standing waves. Let's say that we have a string that has two fixed ends. So that's basically connected to two fixed ends, and we would like to form standing waves on this string. And for this one, basically the boundary condition that we have is that the boundary condition is fixed ends. So fixed ends means we're going to have zero displacement at these ends no matter what. So that means in the standing wave terminology, these ends should be nodes. So if I want to find out what patterns I can observe, we will see that the existence of these boundary conditions leads to discrete patterns of oscillation that we call normal modes. And we're going to find out what those modes are for this scenario. We call these normal modes. And that also implies that we're going to have discrete values of frequencies, discrete frequencies, and that means we have quantization of frequencies. Okay, so let's take a look at what kind of modes are allowed by these boundary conditions. Well, for the simplest possible case, because one end has to be a node, then to go to the next node, I have to go through an anti-node and node. Now you can see this pattern here, node, anti-node, node. Here is the simple harmonic motion of the string elements creating this standing wave. So these string elements are moving up and down and giving me this node, anti-node, node relationship. And basically I see that I have only half a wavelength in between the two boundaries. So therefore the total length of the string must be equal to lambda over 2. So L is equal to lambda 1 over 2. Now if I go to the next possibility, again, remember the boundary condition is that I have to start with a node and with a node. So this is the first one, and then the second one is here. So if you count the distance between two nodes, it's lambda over 2. Two nodes is lambda over 2. So the total distance is one wavelength. And here is the corresponding normal mode here. You can see I start with a node and with a node, and then I have a node in the middle, and this is going to be the distance between two fixed ends will be one wavelength, lambda 2. And I can continue like this. For example, just for exercise, I can go to the third possibility, node, anti-node, node, anti-node, node, anti-node, node, lambda over 2, lambda over 2, lambda over 2. So that would be 3 lambda 3 over 2 must be equal to L, and lambda 3 should be 2L over 3. Now whenever I see a node-to-node section, each section like this I call a loop. So therefore when I look at this oscillation, this is an oscillation in one loop. So here is one loop, and this is an oscillation in two loops because I have node to node, node to node. You can see two loops forming here. This is an oscillation in two loops. And for these modes, I find that the wavelengths are given by lambda n is equal to 2L divided by n for the nth mode, and n is an integer. It's 1, 2, 3, etc. So I find this relationship between the wavelengths of the normal modes that I produce. The index n is basically describing me the nth normal mode. So it corresponds to the nth normal mode. And when I go to the corresponding frequencies, because I have the propagation speed of a wave, it's wavelength times the frequency. So when I write lambda n times fn, I find that the corresponding frequencies will be given by v divided by lambda n, and for this case this will be equal to nv divided by 2l, where n is equal to 1, 2, etc. So these will be called the natural frequencies of these modes. And you can see that I have discrete values of frequencies, so I can conclude that natural frequencies of oscillation are quantized. Okay, so I have this integer multiple relationship. And because for waves on a string, I know the propagation speed, v is equal to square root tension divided by mass per unit length, I can write these frequencies as n over 2l square root t over mu, and n is 1, 2, 3, etc. integer values. So there is something interesting to note here. For all modes, I can write the frequencies as integer multiples of the n equals 1 lowest frequency. So n equals 1 lowest frequency, I'm going to call fundamental frequency. So f1, I will call this fundamental frequency. And I find that the corresponding mode for n equals 1 mode, I can label it as the fundamental mode, or I can label it as the first harmonic, and for n equals 2, I can label it as the second harmonic. So the fundamental frequency is the frequency of the fundamental mode. And because I have this relationship, the frequencies are integer multiples of the fundamental frequency, then basically I can say that because of this integer multiple relationship, these frequencies form a harmonic series. So when I see this integer multiple relationship, I have the harmonic series, and the normal modes are called harmonics. So that's the first harmonic, this is the second harmonic, etc. And the corresponding modes are harmonics. So let's note this here. Normal modes are known to be harmonics. Okay. The frequency of a string, for example, that defines a musical note is the fundamental, and we will see as an example. It can be tuned by playing with the tension on the string or its length. So let's take a look at an example. The middle C string on a piano has a fundamental frequency of 262 Hertz. So the fundamental mode frequency, fundamental frequency for the middle C is 262 Hertz, and the string for the first A above middle C, first A fundamental frequency is 440 Hertz. Calculate the frequencies of the next two harmonics of the C string And if A and C strings have the same linear mass density and length, determine the ratio of the tensions. Now, if you look at inside a piano, you will see that you have strings in between two fixed ends. So basically, I have the same situation that I have described previously. If this is the length L of the string, I must have nodes on the two ends. That's the boundary condition. So if the frequency of the fundamental mode is given, remember for this one, the fundamental mode is node, antinode, node, and lambda 1 over 2 is equal to L. That is first harmonic, or the fundamental mode. Node, antinode, node, antinode, node. That is lambda 2 is equal to L, second harmonic, etc. And for lambda n, I have 2L divided by n. Lambda 1 is 2L, lambda 2 is L, etc., where n is 1, 2, 3, and the corresponding frequencies are given by V divided by lambda n, so it's given by n divided by 2L square root T over mu. So because I have this integer multiple relationship between frequencies, the second harmonic, so if I start solving this problem in part A, I need to know the second and third harmonic of middle C. It's going to be twice F1C. The third harmonic will be 3 times F1C. So this is going to be 2 times 262, which is 524 Hertz. And this is 3 times 262, which is 786 Hertz. So this will be my answer to part A. 524 and 786 Hertz. Now in part B of the problem, I'm looking at the ratio of tensions in the two strings. So I know that the fundamental mode for the middle C has a frequency 262 Hertz, and it's given by 1 over 2L square root tension of this string divided by its mass per unit length, and the fundamental frequency of A is 1 over 2L square root of the tension of this string divided by mu, because it's given to me that they have the same mu and same length L. So what changes from C to A is just the tension. So if I take the ratio of these two, I find that 262 divided by 440 must be equal to square root of the ratio of the tensions, Tc divided by Ta. Therefore, square root of, or Tc divided by Ta is 262 divided by 440 square, or Ta divided by Tc, which is what I have calculated here, is 2.82. Let's look at one more example. One end of a horizontal string is attached to a vibrating blade. So this is my source of waves right here. It's a vibrating blade. It passes over a pulley, as shown in the figure. A sphere of mass 2 kilograms mass hangs on one end of the string. The string is vibrating in its second harmonic. A container of water is raised under the sphere so that the sphere is completely submerged. In this configuration, the string vibrates in its fifth harmonic. What is the ratio? What's the radius of the sphere? So if I look at the first situation, no water situation, the free body diagram tells me that I have equilibrium and this sphere has its weight mg and the tension T. So there is the tension T and its weight mg. So the net force on the y-axis must be equal to 0 because this is equilibrium. So the tension that we have on this string is mg and it is equal to 2 kilograms times 9.8 meters per second square. So the tension is 19.6 newtons. And I see that the frequency of oscillation is the second harmonic, F2. And for the second harmonic here, you can find out that the distance between the two fixed ends is a full wavelength, lambda 2. So lambda 2 is equal to the length of the string. So therefore the frequency is V divided by lambda 2. It is 1 over L square root tension divided by mass per unit length. So it is 1 over L square root 19.6 divided by mass per unit length. So this frequency I have calculated is F2, which is the frequency of the waves that are generated by the source. So the source is generating waves at this frequency. Now I raise a bucket of water underneath, and now my free body diagram changes because I have the weight, I have the tension, plus I have the buoyant force. That's the basically applied by water. That's for an object that's fully submerged, and buoyant force is rho water g volume of the sphere. So it's the weight of the fluid displaced by the sphere. So in my free body diagram, I have mg, the new tension T prime, and the buoyant force B. And still I have equilibrium here, so the net force in y is 0. Therefore T prime plus the buoyant force is equal to mg. So the buoyant force will be given by mg minus T prime. Now I find that it's oscillating in its fifth harmonic. Therefore, I'm going to have, because here the first one will have V divided by lambda 1, which is 1 over 2L square root T over mu. Then for F2 I have 1 over L. For Fn I have N over 2L square root T over mu. For the fifth harmonic I would have F5 is equal to 5 over 2L square root new tension divided by mass per unit length. But because the source has not changed, it has the same frequency. So this must be equal to 1 over L square root 19.6 over mu. So the mu's cancel, the L's cancel, and I find that my new tension has to be 4 over 25 times 19.6 newtons. So therefore the buoyant force is going to become 19.6 minus 4 over 25 19.6. It is 21 over 25 times 19.6 newtons. All right. Now I can basically go to the volume of the sphere, the buoyant force that I have calculated here. So let's take this over here. The buoyant force is 21 over 25 times 19.6. It is density of the water times gravitational acceleration times volume of the sphere. Volume of a sphere is 4/3 pi r cube. So I can calculate the radius. The volume of the sphere is going to be 21 divided times 19.6 divided by 9.8, that's 2, divided by 25,000. So this will give me 1.68 10 to minus 3 meter cube, and that is equal to 4/3 pi r cube. So I can pull r from this equation. It will be 3 times 1.68 10 to minus 3 divided by 4 pi to the power 1 over 3, and I will find a radius of 7.37 times 10 to minus 2 meters. Okay, so the important thing to notice in this problem is that I have two scenarios, no water and with water. So with the no water case, I know that the oscillation is in its second harmonic. I have the second harmonic mode, which tells me the frequency of the source. And when I put the water under the sphere so that it's fully submerged, the tension on the string will change, and I find that the oscillation is in its fifth harmonic. But when I calculate the frequency of oscillation here, it must be equal to the frequency of the oscillation that I calculated initially, because the source has not changed. It must have the same frequency. So I use this relationship between the frequencies in order to calculate the new tension. And when I find the new tension, if I look at the condition for equilibrium, the new tension plus the buoyant force of the water must be balancing the weight of the sphere. And from this equation, I can figure out what the buoyant force should be. And then I use what the information I have about buoyant force, which is it's the weight of the fluid displaced. So it's density of water times g times volume of the sphere. Knowing that the volume of the sphere is 4/3 pi r cube, I can pull